name is Mohammed Mahfouz. I am the program director of the biomedical engineering in the University of Tennessee. I'll take a couple of minutes to explain a little bit why biomedical engineering doing some anthropology work. The story comes, I moved to Tennessee in 2003, and I was approached by a number of students of Dr. Richard Jantz, and they were interested in some of the work we're doing in biomechanics. My background, do surgical navigation, implant design, until now, plus what we're doing with anthropology. So I introduced them a little bit to the concept of Statistical Atlas from our point of view, the clinical and biomedical engineering, and they were very interested, and we started huge collaboration from this point of time till now. So that's a quick introduction to my background. So today I'm going to give a quick outline why we use 3D. And of course, in the morning, Dr. Rossi explained the 3D and their methods of using. We're doing very similar stuff, but in a little bit engineering different way. So the CT principles and then the calibration, I'm going to talk about the modeling and some of the applications. And tomorrow it will continue more in our part of the facial reconstruction. So why 3D? Basically, if you look at the literature, and by the way, that's not only in anthropology, but also in implant design industry, a whole industry, medical device, we're not actually into 3D analysis, but they would do things like calipers, or they make measurements from X-rays, was very common. And I've seen early even anthropology papers doing a lot of work from X-rays. So X-rays come with an inherent problem, of course, which is basically that dense object can shadow structure behind it. And of course, no depth of perception. And if you even don't know how the X-ray was calibrated, projection changed by rotating the object relative to imaging plane. And this is a problem I discovered in the clinical world. I'm going to talk about it a little bit, which when you have even anatomical, like the hip, you have a different angles between people, anaversion, retroversion, go up to 25 degrees. So this, even if you calibrate the X-ray and you want to make measurements from it, still have problems. And of course, limited soft tissue information. And this is kind of an example saying here that you can have an internal structure and you actually cannot identify easily. In some of my work, and I'm going to every now and then explain what I did before so you can get a good background about my work. So some of the work that I did, and probably some of you have heard about or not, but it was a design of the gender knee. This is my design, and the gender hip by Zimmer, and some of the osteoporotic hip stem. And that was part of the work when I initially working with surgeons, and I was in the developer team. I found them using a lot of measurements of what we call in anthropology the neck angle. We call proximal angle. And I found them using a lot of measurements, and I was a little bit disturbed because I know from 3D, and by that time we scanned all vast collection, that this big variation on the neck angle in 3D and also on the orientation. And while they can see example here that the X-ray in a female case, where you can measure it from the X-ray, it's around 142 degrees, but in reality, in 3D measurement, it's 130 degrees, 12 degrees difference. And the same for male, even 13 degrees. So we did a very interesting study where we did actually synthetic analysis, where we rotated a bone some degrees, and then we were measuring, for example, the IM canal and how the IM canal varies. As you can see, you rotate the bone, and then you start getting even different measurements from the projection. And the effect of rotation, where we, this time we were really concentrating on the IM canal because of the size of the hip stem and all that. So we can see that the errors in rotation, and we recorded that we have different measurements. And that this observation came when I've seen them in the operating room, where they make measurements from the X-ray, and then they come and put size. The size doesn't work, and then they move usually a different size, larger. There is always trial and error in this process, and this is what grabbed my attention at the time. And of course, if you use calipers, you can have, and in the morning we heard this, the intra and inter-observer error. And we've noticed this a lot in some of comparative studies that we did. And also can be used for geodesic measurements or linear measurements and limited access to anatomical features. And then internal landmarks, like if you want to look inside the crania, it's very difficult unless you do autopsy. And then limited number of landmarks and time consuming, that even if you add digitizer, still digitizer will give you more points, but you still have some of these limitations. Of course, this is kind of a slide showing you how you do measurement by putting sand, but actually can do it the same way with a computer, with a little bit of computer engineering. You can get the same results with actually higher accuracy. Now, what's CT? And probably a lot of you know CT very well, but I'm going to explain here how we use CT. And also, when we use CT, we come with another set of problems. And I want to explain it a little bit and how we came around this problem. So, of course, the CT, it's an X-ray device and capable of imaging cross-sections and create a stack of images. And each represents a slice. And then this stack can be arranged to create a volume. We have a lot of CT applications, and specifically in my area of implant design and biomechanics, we apply this on the knee, on the lumbar, on the hip, and actually cervical spine too. And some of the CT applications with this, to be clear here, visualization is a very important part. Some of this is showing actually a volume rendering visualization, and this is done routinely if you doing some sort of scans and you look at the workstation of the CT machine, where actually you can, some of these are actually volume rendering with some transfer function to look at specific, whether it's bone or soft tissue, and it's good in our cases sometimes that we actually do segmentation and then compare it with volume rendering to see how good the segmentation quality. Now, the CT history is probably a lot of people know, but actually Sir Hounsfield and Professor Cormack, they started this, and they awarded a Nobel Prize in 1979 in physics, and it's the first time to use a complete digital reconstruction of images completely mathematically. The whole idea is very simple. You have an X-ray source, and then you have an X-ray detector, and this is nothing changed except the technology advanced better than the earlier CT machines. Now, the basic idea, you have 2D views, projections at all angles around the patient, and then you have a rotating source and detector. The attenuation at each detector is basically that what we measure. And these projections are taken together, and there are different type of geometry, which I'll explain. Like you have a parallel, and you have a fan and cone, and I will tell you the difference. So parallel beam was one of the very earlier CT machines, where you have the X-rays coming in parallel, and then the projection on the other side, and then also mathematically the slice is constructed. Fan beam is exactly as the name suggests. It's like a fan beam. You have a point source and detectors. And then the latest, which in, actually not even in the 4th generation CT, but in the 5th generation CT, where they use a cone beam. A cone beam is more, if you hear about small animal experiments, we put the entire animal and do some, take the entire CT of small animals. They use cone beam. Now, they use the cone beam, which is basically look like that exactly on a spiral CT to get it very fast. If you can have very fast, so you can have applications where you want the patient to be motionless and even cannot breathe. So that's the 5th generation that's coming. And of course, when you put the slices together, this is a representation of how when you have one slice, it's pixel. When you stack them together, you create a volume, which is voxel. Now, the CT reconstruction will go the attenuation data from rotating the source and the detector. This is basically projections of the attenuation, and they come in a very small segments. And they go through a mathematical transform, which basically this is how they look on the right, the sinogram, but when combined together mathematically, they create the reconstructed image. Now, some of the CT numbers that we use, it's very important to understand these basics because I will explain later why it becomes very handy from a scan to scan. So typically, a CT slice is 512 by 512. Linear attenuation coefficient measured between the tube and the detector. And the attenuation coefficient measure how X-ray absorbed with the material. So, of course, different material have different absorption. The size of patient also can have some effects. The values in Hounsfield units, and that's how we use it. So the CT number, which is Hounsfield unit, is basically the attenuation of the material minus the attenuation of the water and multiplied by a 1,000 factor. So CT is different a little bit than MRI and other imaging modality from the point has a very large dynamic range. Dynamic range here we means that you have so many gray levels and it depends on up to, for example, 4,000 even more of different gray levels from black to white. So this dynamic range sometimes can affect or can not cause problems, but basically when people work, they like to adjust the two parameters here, which we call the window level and the window width. By adjusting these two parameters, if they are not careful, they could wash away some of the soft tissues if they're looking for soft tissues, or they could wash away some of the bone. And these two parameters can be represented here, like, for example, you have the window level and the window width. You can see if you change, and the window width is basically the dynamic range. So if you reduce or increase the dynamic range, you can actually wash away some of the details. And that's why you need to be careful, and I'll explain how we get around these problems in the scan. Plus, working on the images, you have other problems too. You have the CT parameters that you need to keep track of. So you have acquisition parameters, which determine production of scan data set. And then you have the reconstruction parameters themselves. Acquisition parameters, basically, that's where the CT technologies come in. And I wish that it's standard. Every machine is different. So you have some of the important parameters like the voltage between the cathode and the voltage measured in a kilo electron volt. Higher potential accelerates electrons and thus increase the ray energy. Tube current, it's another important parameter, which is the current flowing through the cathode and measured milliampere. And large current increases number of electrons and thus increase beam intensity. So you have energy and intensity. And in both cases, this is how now most of the new systems would adjust sometimes automatic with the size of the patient and for the quality of image. You also have other things, the scan time taken for tube and detectors to perform complete rotation. Longer scan time increases total X-ray count, and then also the collimation, which is the size of the slice thickness along the z-axis where the motion happens of the tube and the detector. And then, of course, beam filtration, which is different beam shaping filters optimized for different examination. And this is one of the proprietary areas between companies, which they can say, I'm going to do a scan for you for musculoskeletal, or I'm going to do an abdomen scan. They have different parameters that it's not easy to know from machine to another. Reconstruction will have the field of view, which, well, if you did a CT before, they call it the scout, which basically they adjust quick scan of the overall, and then they adjust the window for the region they want to scan. And as I said, the reconstruction matrix 512 by 512. And then you have the reconstruction filter. And again, this is where different filters available for smooth to sharp. I mean, also they have different filters here in the reconstruction. Now, this is create this basically the different configuration, and this is kind of very general, but some manufacturers don't work the same. I try to replicate from GE With Siemens, I had some trouble because of the milliampere. They have different values. So I'm going to say later how we solve this problem. So we have the first generation of CTs, and I don't think any of them exist. If they exist, they used to call them at the time CAT, actually, computerized axial tomography. You don't hear this name again, which was basically single detector, and it translates linearly, and you have and rotates around the patient, and it takes very slow, takes time. And in the past, they used to have misalignment between the slices. I don't think any of this exists now. The second generation, where they start using the fan beam, 10-degree, multiple detectors, so they had better, and the size of the sensor, the detector, increased a little bit, but still slow, 20 seconds per slice. The third generation, this is where they start including the helical scan, and where multiple angle acquisition at each position, and much faster, as you see, 0.5-second rotation. And then the fourth generation CTs, where they have fan beam, static detectors all around the gantry, larger number of detectors which detect the X-ray, and only tube rotates. Now, it's not included here. The fifth generation, we use cone beam, and that's the greatest now scanners. Now, how to solve the problem between different vendors or manufacturers? So we came with this idea a long time ago. So I can't really keep track of all these parameters from machine to machine. And the problem with this, you can find, if you're not keeping track of these parameters, you can end up with the problem I mentioned earlier. You can wash a little bit, you add a little bit, it's not consistent. So the best way is to take these parameters out of the picture completely by using, and we did this constantly, by using Calibration Phantom. The same Calibration Phantom that they use in calibrating a CT machine we use, which is basically something look like that, which have a sample of tissues. In this case, I had the Phantom, which still have this Phantom, runs around 5K, which basically has similar properties to human tissues, this property in these tubes. They have cortical bone, they have trabecular bone, they have lung, same like lung tissues. They have water, and they have, I think, interstitial fluid. So they have different kind. And what we did initially, we used this Phantom for something completely different. It was not anthropology application, but was more of knowing the material and bone density properties of some of the scans. And we put it with the same scan that we are with the specimen or the patient. So basically, we scan in the same time. And as you can see, the three outline here, you have the cortical bone is the one, and then you have the trabecular bone and another kind of material. Now, our initial experiment was to look at cadaver. Here's a cadaver, and you can see the red line going across the cadaver. This is a profile. If you look at this profile, that shows you the lower curve on the left, shows you the intensity profile. And if with the same scan, we did the Phantom on the right. So we knew exactly, because we know in the configuration of the Phantom where is the trabecular bone and where is the cortical bone. And basically, we did actually map the density. So we know the density of these materials, and we mapped it back into the scan, and we had a density map. And this work was important for implant design also, when they want to see how the stem will interact with different tissues. Now, we used it for anthropology from the point of standardizing the scan. So if we use the Phantom with every scan, now it doesn't matter if I'm working with Siemens machine versus GE versus Toshiba. It doesn't matter at this point. It can keep record of the parameters, but it becomes irrelevant to us. So the part of the modeling here, I mean, we did two methods really exist right now. Directly find landmarks or perform measurements on CT slices, and some people do that. Generation of 3D surface model by segmenting objects of interest, then performing measurements on the segmentation model. And that's the method we use with a lot of people. And this method is very similar in its, this big similarity with what the methods mentioned in the morning. The modeling directly from CT slices was a problem, and although you do it a lot in clinical work, but what we discovered in this example, like if I'm going to look at the epicondylar axis, or we call it transepicondylar axis in knee, which is the axis that goes between the medial and lateral epicondyles. And if you measure it directly from the CT, and you're not aware that this axis could come into a number of slices, here what happens, you see in the green here, it's not in one plane. And some people make this problem and take this measurement as if it's length, but they are taking the projection of this line. So it can matter for a few millimeters. That's why you have to be very careful if you're making direct measurements from CT slices. The other approach is to do using segmentation, and then in the segmentation you apply it in statistical atlases, and then this can help us in reconstructing missing data, and then can actually help us in the measurements and landmarking, and then we can run different types of statistical analysis. Every one of these steps we're going to explain right now. So what is a 3D model? It's basically a CAD representation, and it is number of what we call elements or triangular elements, and all these elements are connected together, number of points. So this is the presentation, the vertices. So if I have these vertices represented, it's no different than doing the digitizer and coming into a different vertices. It's the same, but here I have more information. Now, one of our initial applications still going on is to actually use it in segmentation. So this is a scan from our spine application. You can see the 3D models. This is a CT. Since the scan was done for the lumbar, it kind of has a little bit poor quality because that's effect of reducing the radiation on the patient. This is live patient. So you can see here that we can actually have a very good, decent segmentation. So the segmentation, whether it's done automatic or manual, in our case, we do both. So you find the CT image, and here's the problem I mentioned earlier. If you're not aware of if you didn't do calibration and you don't have a phantom, and you change the windows, you can wash out some of the details. You have to be careful. So you have the contour, then the region, and then basically you can recreate the model, the bone model, and then you can have a 3D model. This is some of the earlier segmentation we did for this was for a cadaver I had, and then basically showing the quality of the segmentation. Initially we started manual, now we are doing even automatic segmentation with the help of the Statistical Atlas. So what would the Statistical Bone Atlas, what's basically what I'm talking about here? It's basically generate surface mesh models built from computed tomography data. These new models are converted to a normalized mesh, means that when we build the atlas, we make sure that the number of points distributed properly, and we have control over the number of points. And then models then represented with principal component analysis. Here, principal component analysis is not using the context of measuring statistics, but as a data reduction, because if you start building these statistical atlases to use it later in analysis, they become so huge. So principal component, one of statistical techniques used a lot in anthropology, is used for data reduction, but at the same time capturing the statistics and the modes of variation of a population or of even a bone. And then average bone can be computed from all this bone together. So like in the morning, we've seen the procrastinators taking average vertices. The same here, you have an average bone, which we use to call it a template. Now, this is an example of how the use of Statistical Atlas. So you can have your template bone, which is the average, the red one, and you have a bone, you have a carenia that you want to add it to your Statistical Atlas so you can run analysis on it later. So the entire two models will have a rigid registration where the two carenia models will be aligned. So remember, the red here in this case is the template bone. And then there's something happens here we call surface correspondence. And this is a huge point where, I'll be explained in the next slide, where you have, basically think about it this way. The template model is a kind of a deformable model, will change its shape and become the other one exactly. By doing this, you capture all the statistics. Of course, there are a lot of mathematics behind, which we've been doing for years. By doing this step, you added the other bone into the database or the statistical database without actually having to do anything on its axes. So basically, by this template deforms, captures the statistics, and then basically you have your new bone is added, and at the same time, all its statistics captured in. And we try to get some part of show you how this happens. So if you have the new mesh, in this case, and I apologize for shifting the colors, but this is the new bone that you want to add. And your base mesh, as the green, is a template. So basically what happens here is you have the new bone coming because someone did it. It may come from different source, not your lab, another lab. Someone did segment the bone, and they segment the skull has thousands of different points, while your base template may not have the same number of points. So usually what will happen is you will have number, when we put them together to register, you will have number of vertices competing on the same. So what we do is we do what's something called mutual correspondence, which basically redistribute these points, but the redistribution comes from the base mesh. So these three bones will be average, and then the closest one, and replace many to one relationship with the mean, and then that's iteration, and then we take the base mesh, and then we try to do the same thing, but in this case, try to come to the closest point on the new mesh. Okay, and then along with weighted combination of vectors, this process can reiterate back and forth until the entire vertices distribution of the base of the template becomes very close with a threshold, very small threshold to the new bone or carenia, in this case. Okay, so by doing this, we actually capture this carenia into our statistical atlas. Now, this is where we differ completely from the Procrasti method that was described in the morning. Completely. In this case, we have a full control because now we have full control of the vertices, and we can make all the measurements we want. In the feature extraction, we divide them into two parts. Part we call the statistical, the shape model, and the specific landmarks. And we call them global because the shape is global. The shape will be very similar. So that's a global of the model. And then the specific landmarks, this is local measurements. All right, so the statistical representation, landmark-based. The disadvantage, manually defined landmarks, time-consuming, high intra-observer error. And what we're saying is by doing the steps, and we will explain tomorrow, we can automate this entire process. So we don't have really to go and try to find the different landmarks. It's completely automated. But you have at the beginning, of course, someone need to go and check. You have to do still, the anthropology people will come and check to see whether this is, we have errors or whether it's working properly. The surface base is the advantage perform the entire bone surface after establishing correspondence. Correspondence is the key word here. And in this case, we don't have 21 or 71. We have anywhere we want to measure, we will measure. Quick and convenient method, eliminate subjectivity and only done once. The point I forgot to mention. Have 500 bones, 500 skulls, like some of the studies with NIJ we do. Do I go and measure in every one of them? Then that defeats the purpose of what we're doing here. The whole idea here is we can do the measurement once and propagate it across the 500 bones or 1,000 bones. That's the purpose here. And basically can go back and then look, because once you identify the landmarks you want, you can propagate the measurements. Then you can go and randomly select and bring, for example, someone and make a comparison measurements. Because if you do this and you have thousands of carenia, that can take forever. I mean, some of the earlier work that we did, and also a good part about doing it this way, that you can identify area with high variation. A number of PhDs came out of Tennessee using my methods in identifying clavicle, some areas of the bone. Some people did analysis on Lucy bone. I mean, not number of people work. And this is example. So the color code tells you the high variation. So after doing this, you can rank the population and look at the areas for high variation. And then you can go after these areas and study it more. One of the earliest things we did when I started my relationship with Richard Jantz is he brought me this bone. This bone was discovered washing on the river in Tennessee, and the police didn't want to investigate. And he said, what can you do about it? So make your estimation. So I took this bone, and we did the CT scan, and we came up with the right estimation of the height and even the gender. And he was right. I told him this is a female, and it turned correct at the end. The DNA test was done, was confirmed, and case closed. So this was done 2003, 2004. My first interaction with anthropology at UT. Some of this work could be easily actually, and we're doing right now, is use it with fragmentary bone reconstruction. And here what we have in cases like that where you have missing bone, now if you have a statistical atlas, it's very important when you have statistical atlas is, I want to use the correct terms. You don't call it race or ethnicity, what do you call it? I forgot. Ancestry, okay? So to build, we still, I mean, if I use, I think I was writing clinical paper the other day, so they moved everything I put about anthropology, and they moved it back to gender or race, or so we kept it the way they want clinical. But actually, the funny thing is they removed ancestry, removed all this. But anyhow, that could help in really filling the missing information and fragmentary bone. And there is a big initiative going on in my group and with some people at Anthropology, Richard Jantz and Natalie, and working through fragmentary bone is try to use this as a template. We did some work before. Adam and I worked with Adam Sylvester. We did this, like he was very interested in these methods, and he brought samples of Lucy, Stropithecus africanus, and we tried, and it actually did work very well. We published this paper using the same methods in paleoanthropology, although it wasn't my interest at the time, but I got very interested in this. So one of our clinical applications, very important, and here this is the work of Dr. Imam here, is pelvis reconstruction. Basically, why not? In clinical, I have a severe problem with people that already their pelvis completely deteriorated. They can't put implant for them. They can't put cup. They can't. I mean, it's something like that. So we have also big work, and I did put some patent application on some of the software here, is how we can really reconstruct, build a cup for the patient and standardize this process, because they are in a very bad shape, and only a handful of surgeons in the country, they do this kind of surgery. And here is the process. You get the training data, you get the atlas, reconstruct the pelvis, you get a new patient in, you get defect classification, of course, landmarking and measurements, and then the statistical analysis. But basically, this is how you construct kind of a cup or an implant for this severe cases. We did our other grant also with the automatic measurements of the skull. Our results right now, and we publish and will publish later the full results, because we did increase the sexing for males and females 98%. I'm not sure what the highest right now. That's independent of any other bone. That's only directly on the cranium. And also, we're taking the thickness measurements. The other work is not the purpose of this workshop, but they can overlap because part of our work in increasing this percentage of discrimination and basically including some internal features and trying to project it with X-ray. So if you have a skull that you don't want to destroy it, but you can relate some of these parameters together and come up with the proper identification. Now, we did previously work on the patella, and we published this work in International Forensic a few years ago, where we took 45 different measurements on the patella. And basically, this is the paper published 2007. And then the results were, I think, 93% in some cases with additional information was 96%, where we had, like here, you see the confusion matrix where you have predicted correct 28 and 2 wrong, and we predicted 44 males and 3 wrong, and that's basically the to test the software. And that's basically some of our work. And if you have any questions, please. Okay.
Is it like a control?
It is control, absolutely. The Phantom has, I can go to the slide. The Phantom basically, this is a standard Phantom that technologists here use in calibrating CT machines. So they want to see the intensity, the energy, so they want to calibrate. But it is basically, I wish I brought it with us. It's a kind of a platform, has, these tubes have material similar to soft tissues. So you can run it with the scan, actually. With the scan, here how it goes. You put your scan specimen, was a cadaver. Even with live patients, I use it too. So if you put your cadaver, you put your bone, whatever, and the technologies will play with all the parameters I mentioned, intensity, window, all these parameters. And once he's done, and the scan goes on, it will be applied also to the Phantom. So now you have your sample and the Phantom together. So it's kind of control and takes away that you have to worry about doing the same scan with a different machine. So you go another machine, use the Phantom. So in this case, you don't have to worry. Now you can adjust the intensity level like this curve. So you adjust the intensity level. Then in this case, you normalize the scans between the machines. So you don't have to worry about all the parameters.
For the automatic detection of the landmarks, I know you've done research on this. It's really interesting. Are you moving towards an application that people can buy, a program that anthropologists can
Yes,
use?
what we're doing right now in the grant that I mentioned about the measurements, we will put some data, but it was not required to transition a software, but we actually applied for a continuation where we put a complete software like for this, something like that, but it's 3D. So basically, similar to what you have, but it's not limited only to digitized data. You can do it if you have a scan, you bring it in. It doesn't matter. We're actually, we put a full, complete proposal to do that and have it online. I will have some elements online, but not the full-blown because it's kind of a big application, yeah.
Mohammed, on the morphological differences slide 49, you have low variation and high variation. Do you have numerical values for that?
We have numerical values. We always put this legend here. So I'll come to it. When we do it is based on ranking. It's some of the work here, if you know Fisher discriminant ratio, that's basically how it ranks the variation. So it's easier for us we have numbers, but it's easier for us to say, okay, point to me the area where you have the highest variation. So for example, the high variation, you look at the areas and it comes very consistent, like the epicondyles, you look at the femur here. This is where we see actually the most variation between men and women. And the Fisher discriminant, it's a discriminant analysis. You can do it, for example, between males and females. But multiple discriminant, you can do it across population, different ancestries. I was going to say population. So you can do this across multiple discriminants, a little bit like, say, the general case of Fisher, which can compare between two different two groups.
If you're reconstructing, like on the one where you had a female that was missing the distal end of her femur, and you reconstruct that, and that's an area of high variation, how do you choose the reconstruction parameter?
The reconstruction is done automatic. Here, what happened in this case, only what we had is partial. We have the proximal. The distal was completely missing. But the atlas, you can divide it any way you want. So for example, you can have an atlas for the entire femur. We have for the entire femur. We have for the distal by itself. We have for the proximal. And you can look at the shaft has a low variation, a little bit, unless you are looking at the isthmus or looking at the IM canal. So we know that every atlas has its own weights. So we build from statistical inferences, we can actually predict the proximal part has weighs more information than the distal. So we can have a good, precise prediction. Actually, we came with, from this prediction was the exactly height of this woman was 5.2 when we estimated was correct, actually from records. So, multiple, you can look at the bone as one bone. You can divide it into multiple areas, and then you can have even multiple statistical atlases on different parts of the bone, like distal, proximal. In the pelvis, for example, is divided into a number of areas. Same for carenia. So I mean, that's how we give weight. So it's weighted that, okay, from our work, we can predict the entire bone from either partial, from distal or proximal or part of the shaft. Now, of course, that will it's completely different when you have the full femur, which you have more information, but can give you a good idea up to what 98% of the bone. We have a very good, decent results on long bones. I think we're beyond the long bones right now because we did a lot of work on long bones, and I designed implants. I did everything with the long bone. Now we're moving into the more complicated areas like carenia, lumbar, pelvis is really difficult, where you have the bones more complicated in structure, so it's not a long bone. So.
So Mohammed, on this one with the femur, so then what equation did you use to determine 5'2"?
I used the best equations, in the same equations in the morning, the same one exactly.
So you get a range then, not just an exact statue.
Yeah, range. No, it was range. But what we did is we came up with the height, I mean the length of it. And we plugged it in the equation. So I'm not working on prediction. I'm using the existing equations, but we are predicting the 3D structure. So now the trick here is you can say whether what kind of ancestry it is, European or so you can play with different. But now for us we have a good understanding of the European and black, and so we have good. But this took years to come to this point.
Out for the day? Thank you.
Okay. Thank you very much.